Module number 3, multivariable calculus. In this module, we will extend the concept of definite integral to functions of two and more variables. Now, evaluating double integrals. A partial derivative of a function f of xy are calculated by holding one of the variables fixed and differentiating with respect to the other variable. Now let us consider the reverse of this process, partial integration. So that simple symbols, integral from a to b f of xy dx and integral from c to d f of xy dy denoted by denote partial definite integrals. So the first integral from a to b f of xy dx, differentiating the function f of xy, the two variable function, with respect to integrating the function with respect to x, treating y as a constant function, and called partial definite integral with respect to x. So we will evaluate this value by fixing the value, integrating with respect to x, and we'll fix functions of y or y as a constant function. Similarly, integral from c to d f of xy dy, integrating the function f of xy with respect to y, treating x as a constant function. For example, integral from definite integral from 0 to 1 x y squared dx. So integration with respect to x, treating y as a constant function. So y square is a constant function. Integrate the function with respect to x. Integral of x equal to x square by 2 into y square from 0 to 1. So y square by 2, x varying from 0 to 1. So 1 square minus 0 square is equal to 1. Y square by 2 will be the answer. Similarly, integral from 0 to 1, x y square dy, integrating the function with respect to y, treating x as a constant function. So x is a constant, integral of y square, y cube by 3. And the limit of integration from 0 to 1. Answer is x by 3. So a partial definite integral with respect to x is a function of y. Partial differential of a function f of xy with respect to x is a function of y. Similarly, a partial definite integral with respect to y is a function of x. So this two-stage integration process is called iterated or repeated integration. Now we introduce the following notations: integral from c to d, a to b, f of xy, dx, dy. That means we'll integrate the function f of xy with respect to x first. So if we integrate the function f of xy with respect to x from a to b, we'll get a function of y. As we can see here, the integral of f of xy dx from a to b is a function of y. Then we'll integrate the function f of y with respect to y. Function of y with respect to y from c to d. Similarly, integral from a to b, c to d, f of xy, dy dx. First integrate the function with respect to y. We'll get a function of x. Then integrate that function with respect to x. And these integrals are called iterated integrals. So we'll move on to some examples. Integral from 1 to 3, 2 to 4, 40 minus 2xy dy dx equal to first one, which is equal to, first integrate the function 40 minus 2xy with respect to y, treating x as a constant function. So integral of 40 with respect to y is equal to 40y minus 2xy, integral of 2xy with respect to y. 2x into y square by 2, 2 get cancelled, equal to xy square from 2 to 4. Integral, limit of integration 2 to 4. Upper limit minus lower limit, that is 40 into 4 minus x into 4 square, that is 16, upper limit minus lower limit y equal to 2. 14 into 2 minus 2 square, 4 into x dx, which is equal to 80 minus 12x. Now integrate the function with respect to x. 18x minus 6x square from 1 to 3, which is equal to upper limit minus lower limit. You will get the answer as 112. Similarly, integral from 2 to 4, 1 to 3, 40 minus 2xy dx dy. First integrate the function with respect to x, treating y as a constant function. So 40x minus x square into y. X square by 2 into 2, 2 get cancelled. So x square y from 1 to 3 dy equal to upper limit 120 minus y equal x equal to 3, 9y minus lower limit 40 minus x equal to 1, 40 minus 1 y, 40 minus y dy, which is equal to 80 minus 8y dy. Integration from 2 to 4. Integral of 80, 80y minus 4y square by 2, 2, 8 get cancelled, equal to 4y square from 2 to 4. Again, the answer is equal to 1, 1, 2. So as you can see from these two examples, integral from a to b, c to d, f of x, y, dy, dx equal to integral from c to d, a to b, f of x, y, dx, dy. That means if R be a rectangle defined by the inequalities a less than or equal to x less than or equal to b, c less than or equal to y less than or equal to d, then, or if f of x, y is a continuous on this rectangle, then integral limit of integration can be interchanged. Double integral over the rectangular region R f of x, y, dA equal to integral from c to d, a to b, f of x, y, dx, dy equal to integral from a to b, c to d, f of x, y, dy, dx. That means we can interchange dx and dy and limit of integrations, provided if the region of integration, if it's a rectangle, then we can interchange. And this theorem is called Fubini's theorem. Double integral over double integral c to d, a to b, f of x, y, dx, dy equal to double integral a to b, c to d, f of x, y, d by dx. And remember, this is only for rectangular regions. Now another example. Use double integral to find the volume of the solid. Before going to volume, we'll discuss another example. Evaluate the double integral. Double integral over R, y square x dA, where R is the rectangular region defined by set of all x, y, such that minus 3 less than or equal to x less than or equal to 2, 0 less than or equal to y less than or equal to 1. So, double integral over the rectangular region R is defined by x varying from minus 3 to 2. X varying from minus 3 to 2, y varying from 0 to 1. So first we'll integrate the function y square x with respect to x and the limit of integration minus 3 to 2. Then it will be a function of y. Then we will integrate that function of y with respect to y. Limit of y is equal to 0 to 1. So double integral over the rectangular region R is equal to double integral over R y square x dA equal to 0 to 1, integral from 0 to 1 minus 1 to 2 y square x dx dy, which is equal to integral from 0 to 1 y square into integral of x square by 2 from minus 3 to 2 dy, which is equal to integral from 0 to 1 upper limit minus lower limit, which is equal to minus 5 by 2 y square dy. Again integrate the function with respect to y. minus 5 by 2 into y cube by 3, which is equal to minus 5 by 3 into 2 equal to 6 y cube from 0 to 1. Upper limit minus 5 by 6 into 1 minus 5 by 6 into 0, which is equal to minus 5 by 6. The limit of integration or double integral over r y square x dA is equal to minus 5 by 6. So this integration, which is also equal to double integral over r y square x dA equal to integral from by interchanging the order of integration, we can directly write integral from minus 3 to 2, 0 to 1 y square x d by dx. Both will give you the same answer, since the region R is a rectangular region defined on a rectangular region R. By using Frobenius theorem, you can interchange the order of integration. Now, some properties of double integral. First one, double integral over R c into f of xy dA is equal to c into double integral over R f of xy dA. That means constant can be taken as a common factor. Then double integral over R f of xy plus g of xy dA is equal to double integral over R f of xy dA plus double integral over R g of xy dA. Similarly, for subtraction, f of xy minus g of xy equal to double integral f of xy dA minus double integral over R g of xy dA. And if R is a region which is subdivided into two regions, say R1 and R2, if f of xy is non-negative on a region R, then subdividing R into two regions, R1 and R2, has the effective of subdividing the solid between R and z is equal to f of xy into two solids. Double integral over R f of xy dA is equal to double integral over R1 f of xy dA plus double integral over R2 f of xy dA. As you can see here, double integral over R f of xy is equal to double integral over R1 plus double integral over R2 f of xy dA. Now, the meaning of double integral over R, geometrical meaning is double integral over R f of xy dA. That means it is the volume of the solid bounded below by the region R and above by the function f of xy. Double integral over R. So if R is a rectangular region, then double integral over R f of xy dA is area of the volume of the solid bounded below by the rectangular region R and above by the function f of xy. So in this case, R is a non-rectangular region. Double integral over R f of xy dA, it is the volume of this solid bounded below by this region R and above by the function f of xy. So volume of R, which is equal to volume of R1 plus volume of R2. That means we can subdivide this region into two, R1 and R2. Then double integral over R1 f of xy dA plus double integral over R2 f of xy dA will give you the volume of the solid f of xy, volume of the solid bounded below by the region R and above by the function f of xy. So volume of the entire solid is the sum of the volumes of the solids above R1 and R2. Now double integral over non-rectangular regions.